I know we're continuing centripetal motion, but from the last time we did centripetal motion, which was on Thursday morning, in the past 2 days, the notes have been completely rewritten and they look very different. So I think it would be better if we actually start from the beginning and see how the notes have been rewritten, while the examples remain the same, but they also have gotten a bit of changes. Yeah, so we might actually take slightly more than 1 hour, but we should be able to finish. Okay, since most of the other stuff we have already looked at already. The title, of course, has changed from Centripetal Acceleration and Force to just Description of Centripetal Motion, so that bit has changed. The objectives are still remain the same. The Centripetal Acceleration, how this bit is the same, but as we mentioned earlier on Thursday, to say when we are talking about centripetal acceleration, basically we are talking about an object moving with a constant speed, but it's moving in a circle. So the fact that this particular object is changing direction, that's where the acceleration comes from. The acceleration is not coming from the fact that the speed is changing. The speed does not change. The speed is constant. So we have an object moving with a constant speed, but it's moving in a circle, and therefore that's where the acceleration is coming from. And yeah, so this acceleration is towards the center of the circle. That's why the centripetal comes in, and the centripetal acceleration AC is given by the speed of the object moving in a circle, v squared divided by r. So that bit is what we saw on Thursday. Okay. We also know that the speed of an object moving in a circle, or the tangential velocity, is related to the angular. So is related to the angular velocity, and as follows. So v, which is a speed, is equals to the radius of the circle multiplied by the angular velocity, like this. So if we substitute for v, which we have here, v squared, we substitute for v there, we put r omega, so we end up having AC is equals to r omega, this whole thing squared, divided by r, so we end up having AC we end up having equals to r squared omega squared divided by r. This r divides one of the r's there, cancels one of the r's there, we end up having AC, which is centripetal acceleration, is equals to also the radius of the circle multiplied by omega squared, which is how fast the thing is moving in a circle. So there are two ways of actually finding what the centripetal acceleration is. So you've got AC equals to v squared over r, and also AC being equals to r multiplied by omega squared. This bit we saw on Thursday. The other thing we saw on Thursday was that if an object is undergoing acceleration, there must be a force which is causing this particular object to undergo acceleration. So you have an object of mass m, but the mass is not the reason why the object is undergoing acceleration. Whenever an object is accelerating, there has to be a force which is causing that acceleration. In this case, the acceleration which causes an object to undergo centripetal acceleration, that's what's referred to as centripetal force. And centripetal force, according to Newton's second law of motion, F is equals to ma. Since we know the acceleration, we also know the mass. The centripetal force is going to be given by Fc, is going to be equals to the mass of that particular object multiplied by the acceleration AC. In the case where our centripetal acceleration AC is equals to v squared over r, so you end up having the centripetal force Fc equals to the mass. So then where there is this centripetal acceleration, you substitute for v squared divided by r, so you end up having your centripetal force Fc being equals to the mass times the velocity squared divided by r. That's the first thing. We have also seen that the centripetal acceleration AC is equals to the radius of the circle multiplied by the angular velocity, which is how fast this particular object is moving in a circle. So if we do that substitution here also, we can also have another expression of the centripetal force, which is equals to the mass of the particular object multiplied by the radius omega squared, and this basically is going to give us what we have here, the centripetal force being equals to the mass, the radius, and omega squared. So there are two ways for you to work out what the centripetal force is. The centripetal force Fc is equals to the mass velocity squared divided by r, and the centripetal force is also equals to the mass, radius, omega squared. this bit here. This is what we did. So this is almost similar to what, basically it's, apart from the numbers, it's exactly what we did last time, if I'm not mistaken, but stuff has been written a bit. Okay, the thing which has been completely rewritten is the addition of this section, the different phases of centripetal force. So basically what centripetal force per se is not, it comes in different forms. It's provided by different forces depending on what the circumstances are. For example, kinetic friction force. Kinetic friction force can provide centripetal force, especially in the case where a car is going round a roundabout. So if you are going round a roundabout, your ability to go around the roundabout depends on the friction between the tires and the roundabout. And that friction is what is referred to as kinetic friction force, since the car has to move. So in this case, when you've got a car going round a roundabout, the centripetal force is provided by the kinetic friction force. So the centripetal force Fc, which is the force keeping your car on a roundabout, is provided by the kinetic friction force. Now, since you're talking about kinetic friction force, we know that friction always depends on the coefficient of friction. So in this case, our coefficient of friction is the kinetic friction. It also depends on the normal force. The normal force is just equal to the weight of that particular car which is moving around about. So our friction force, Ff, is going to be equal to the coefficient of kinetic friction multiplied by the normal force. Since as the car is going round the roundabout, it stays on the roundabout, it doesn't jump up and down, then we know that from that bit, we know that the normal force is equal to the weight. So if you replace the normal force with the weight of that particular car, whatever object is going around the roundabout, we end up having a friction force which is equal to the coefficient of kinetic friction multiplied by mg. So this is our friction force. So this friction force is the one which is providing the centripetal force. So in that case, from what we have up here, Fc, which is equal to the friction force, we can equate these expressions. This other bit side, this is our centripetal force in terms of mass. The speed squared and divided by the velocity is equals to mu k mg. As you can see, there is mass on this side, there is also a mass on this other side of the equation. So we can cancel out the masses. When you cancel out the masses, you end up having v squared is equals to r equals to the coefficient of kinetic friction multiplied by g, which is acceleration due to gravity. If you multiply on both sides by r, you end up having v squared is equal to the coefficient of kinetic friction, the acceleration due to gravity, and the radius of the roundabout. Since we are interested in the velocity with which you are supposed to drive around this roundabout, we take the square root on both sides, so we end up with v is equal to the square root of the coefficient of kinetic friction, g, and r. So this is the expression, equation number 15, is the expression which determines what is supposed to be your maximum speed as you go around a roundabout. Is it clear? So as you can see, we have rewritten the same stuff in a different way so that the physics can come out. Is it clear?
Yes, sir.
Okay. So this is when an object is going around a roundabout or something will look similar to a roundabout. So we have our example here. The first example, which one of the examples we had, is now the first example. What is the maximum speed at which a car can round a curve of radius 25 meters on a level road if the coefficient of static friction between the tires and the road is 0.8? So in this case, we are talking about the same thing, because we are talking about maximum. If we're talking about maximum speed, then your coefficient, this bit here, will have to change. It will become the coefficient of static friction. So in this case, you have your velocity is going to be equal to the square root of the coefficient of static friction multiplied by g multiplied by r. And basically that's the expression which gives us our maximum speed. So V is going to be equal to the square root of the coefficient of static friction multiplied by G multiplied by R. Our coefficient in this case is 0.8. Our acceleration due to gravity on Earth is 9.8. The radius of the roundabout is the radius not of the now this is not a roundabout, but the radius of the cave is 25. We derived for the roundabout, but it also applies for a cave because a cave is part of a circle. So basically, this expression which we have, V is equals to the square root of the coefficient of friction multiplied by G and R, applies to any object, any car, any bicycle, any motorcycle which is going around in a circle. Okay, so in that case, when we substitute, we end up having V is equal to the square root of 0.8 multiplied by 9.8 multiplied by 25. We end up having a velocity V which is equals to 14 meters per second. Is that clear?
Yes, sir.
Okay, next, apart from kinetic friction, you can also have a case where the static friction force is the one which is providing the centripetal force, like in this case here, where you have a ring which is rotating at an angular velocity omega. Then inside this ring there is this little mass here. This mass, this cube has got a certain mass, but this cube, because the ring is rotating so fast, this cube is being prevented from slipping down like that, so it doesn't fall. So it stays inside the ring. It's not glued, it's just there, but it's staying inside the ring because the ring is moving, rotating at a certain particular speed, which is omega. So what we would want to find out in this case, where you have got the reason why it's not moving is because there's friction, which is static friction, which is keeping it in place. We want to find out with what velocity, with what angular speed should this ring be rotating so that this mass stays in place. So we are talking about the rotation of the ring. So in this case, if we do that, since we know we're interested in the angular speed of the ring, we can work out the centripetal force. Fc is equals to the mass of the object which is moving in a circle multiplied by the radius of the ring multiplied by how fast the ring is rotating, omega squared. Since the centripetal force is being provided by the static friction, because our object doesn't move, that block doesn't move, therefore the friction force is going to be equal to the coefficient of friction force multiplied by the normal force. Then also we know that the normal force is equal to the weight of that particular cube, so that's going to be the normal force is going to be mg. Therefore our friction force, our static friction force, is going to be the coefficient of friction multiplied by the mass of that particular object and g. So we end up having this expression here. Therefore when we have our centripetal force, which is the mass, radius omega squared is equals to the coefficient of static friction, the mass, and g, like that. So in this case, what do we have? We have got the mass of the object this side. We also have got the mass of the object this side. So we can cancel out the masses. When you cancel out the masses, you remain with r. Omega squared is equals to the coefficient of static friction multiplied by g. Since we are interested in how fast this particular object is rotating, we are going to divide both sides by r. So when you divide both sides by r, we end up with omega squared is equal to the coefficient of friction on top multiplied by g divided by r. Then when you take the square root on both sides, we end up with omega is equal to the square root of the coefficient of static friction, then g divided by r. So this is the expression which gives us how fast our ring is supposed to be rotating if that particular mass which we have there, that particular block, is not to slip. So you have to use this expression. Omega is equals to the square root of the coefficient of static friction multiplied by g divided by r. Equation number 22. Are we clear?
Yes, sir.
There must be a tutorial question. Is there, I think, something along these lines somewhere. I don't know whether it's for the other course or like that, or this one, okay. As shown in figure 1, which is this figure 1 which you have here, as shown in figure 1, a bob stuck to a rotating ring, a cylindrical shell of inner radius r equal 1.5 meters rotates at an angular speed omega. A wooden block rests against the inner surface and rotates with it. If the coefficient of static friction between the block and the surface is mu s is equal to 0.3, how fast must the shell be rotating if the block is not to slip and fall? So we are looking for the speed. How fast is the ring supposed to be rotating? And we have got this expression here. So the whole thing is related with this. So our coefficient of static friction is 0.3. Our acceleration due to gravity is 9.8 meters per second, and the radius is that. So if we substitute in here, so we end up with omega is equal to the square root of 0.3, 9.8 meters per second squared divided by 1.5, like that. So you end up with omega being equals to 1.4 radians per second. Are we clear? That's how fast your ring is supposed to be rotating. Is it clear?
Yes, sir. Yes, sir.
Okay. So we are showing the physics, then we use that physics to work out an example. So that is with what is friction. So both kinetic and static friction, they can provide centripetal force. The other force which can provide centripetal force is what's called the gravitational force, or the force of gravity. And the force of gravity is always worked out this way. The force of gravity, or the gravitational force, is equal to G, then the product of the masses which are involved in this attraction, then divided by the distance of these particular objects from their centers, where Fg is the gravitational force, then this G is what's called the gravitational constant, or Newton's gravitational constant, and this is what the gravitational constant is. Then m is the mass of the first object, then m2 is the mass of the second object, then r is the distance between the two masses. Our interest in this gravitational force as a source of centripetal force, is with the use of satellites. We have satellites which provide telecommunication going around the Earth. So in this case, as you can see from this little diagram here, this schematic which you have, we have a satellite up in space, and these satellites in space move with very, very high speed. But as they are moving with very high speed, this line here is showing the orbit of the satellite. So satellites move in circles, especially low Earth orbit satellites. They move in circles like that. So the satellites in space are always forced to move in a circle. If the satellite is being forced to move in a circle, there has to be a force, as you can see from this line here, F. There has to be a force which is providing the centripetal force. The centripetal force in the case of spacecrafts like satellites or the International Space Station, which goes around the Earth every 90 minutes, because the IS, the International Space Station, goes around the Earth every 90 minutes. The centripetal force keeping it like that, forcing it to move in a circle, is provided by the force of gravity. And the distance between the spacecraft and the Earth is measured from the center of the Earth all the way up to where the spacecraft is. So this R you're seeing here, which is the radius of the orbit is made up of the radius of the Earth plus the height of the spacecraft above the Earth. So you've got the radius of the Earth plus the height of the spacecraft above the Earth, like that. So in that case, your centripetal force, Fc, when you have a satellite moving in space, your centripetal force, Fc, is going to be given by the mass of the satellite, which is ms, multiplied by the speed of the satellite in space, which is v, divided by the radius of the satellite's circular orbit. The radius rs of the satellite is made up of the height of the satellite above the Earth and also the radius of the Earth, rs. So here with ms is the mass of the satellite, V is the speed of the satellite in space, and R is the radius of the satellite circular orbit, like that. Now, our centripetal force is being provided by gravity. So in this case, this is gravity. As you can see, we've got two masses. There is the Earth, which is one mass. There is also the satellite, which has got its own mass, ms, mass for the satellite. Then there's also the mass for the Earth, which is a planet or some big body which is bigger than the satellite. So in this case, your force of gravity can be written as G, which is a gravitational constant, multiplied by the mass of the satellite, ms, multiplied by the mass of the planet. It can be Earth or it can be any other planet where human beings have sent satellites. For example, we have been sent people, rich countries, the US, the United Arab Emirates, the Chinese, they have sent satellites to Mars, and that's how they work. They stay around Mars like that using this expression. Okay, so where G is 6.674 times 10 to the power minus 11 meters cubic kg per second. Then ms is the mass of the satellite. Then mp is the mass of the planet this particular satellite is going around. Then rs is the radius of the satellite's orbit. So since we have our centripetal force as this bit here, this is our centripetal force for the satellite, and this centripetal force is being provided by gravity, Fg. We equate these guys, so we end up having Fc equals to Fg. So we end up having the mass of the satellite times the speed of the satellite in space divided by the radius of the satellite circular orbit equals to the gravitational constant, the mass of the satellite, the mass of the planet, divided by the radius of the satellite orbit squared, like this. As you can see, on both sides there is ms, there's a mass of the satellite this side, there's a mass of the satellite this side. So that ms can be cancelled out, but there's also rs here, there's rs here, then you've got rs squared here. So you can cancel out ms and rs. When you do that, you cancel out this bit and that bit, then you cancel out r and one of the r's, you end up with v squared is equals to g, which is a Newton constant, multiplied by the mass of the planet, then divided by rs. Since we are looking for the speed with which our satellite is going to be moving in space, then we take the square root on both sides, so we end up with v is equal to the square root of g multiplied by the mass of the planet multiplied by rs. So from this expression, you can see that the speed of your spacecraft or your satellite in space depends very much on the mass of the planet. If the planet is large, then things will always tend to move faster around this particular planet. Spacecraft, satellites, and other things will always tend to move faster around this particular planet. So this is the expression which gives you your velocity of the spacecraft. Are we clear? And rs is the satellite's circular orbit, which is made up of the radius of the planet and also the height of this particular thing around above the planet. Are we clear? I think we went through something like this, and this particular example, I think we went through it, but things have been rewritten. Is there any question? Are we clear?
Yes, sir.
Okay, so here a spacecraft orbits the moon at a height of 20,000 meters, assuming it is to be subject only to the gravitational pull of the moon. Find its speed and the time it takes for one orbit. For the moon, the mass of the moon is 7.34 times 10 to the power 22 kgs, and r is equals to the radius of the moon is 1.738 times 10 to the power 6. So with this information, we have the mass of the moon, which is what we need, because we need the mass of a planet. That planet can also be a moon, as long as you've got a body around which this particular satellite is going. So the mass of the moon, we have it, we need it. The other thing we need is this bit, RS, which is the circular orbit of the satellite. This circular orbit of the satellite is made up of the radius of the planet or the radius of the moon plus the height of the satellite above the moon. So in this case, we have the radius of the moon, which is this one, then which is going to be the radius of the planet, and also we have got the height of the moon, of the satellite above the moon, which is going to be our h, so that we can get our RS like that. So when you do that, RP is the radius of the moon and h is the radius of the spacecraft above the moon. So when you do that, you end up having RS is equals to 1.738 times 10 to the power 6 plus 20,000. You end up having RS is equals to 1.758 times 10 to the power 6. So now that we have our RS, we can work out what the velocity is supposed to be. The velocity is equal to the square root of g multiplied by the mass of the planet multiplied by RS. So in this case, our g is this one here. The mass of the moon is that bit here. Then the radius of the circular track of the moon is this. So you end up with the v, which is equals to 1,669 meters per second. So this is the speed with which the craft is going to be going around the moon in space. Are we clear?
Yes, sir.
Okay. The other question we need to answer is how fast the time it takes for one orbit. Now, one orbit is a spacecraft going round in 1 cycle. So basically, how much time does it take for this spacecraft to do one revolution? So for one revolution, the angular displacement is known. It's just 2 pi radians. So in this case, with this velocity, which we have, we change this velocity. We want to change this velocity into angular velocity. We know that if you've got the speed v, then you can work out what the angular velocity is going to be. We know that v is equals to r s, which is the radius of the circle in which the satellite is moving, multiplied by omega. So we can find omega. In this case, omega is equals to v divided by rs. So that's going to be omega is 1,669 meters per second divided by this rs. Then you end up with our omega, which is equals to 9.5 times 10 to the power minus 4 radians per second. So this is how fast we have got the speed in meters per second, and we have got how fast the craft is going. Now, why do we need this? The reason why we need this is because the angular velocity of a spacecraft, or the angular velocity, is related to the time it takes something to go around in a circle. If you recall from the beginning of our course, we expressed our angular velocity, omega, in terms of frequency, as omega is equals to 2 pi f, where f is a frequency. But we also know that from our definitions which we did, that the frequency is just the reciprocal of the time it takes to complete a revolution. So we end up having this. So we end up having omega is equals to 2 pi multiplied by 1 over t, where t is the period or the time it takes is going to take the spacecraft to complete an orbit. Therefore, we end up having our omega, which is equals to 2 pi divided by t, which is the period. What we are looking for is this time, t. So we make it the subject of the formula. When we do that, we end up having t is equals to 2 pi divided by omega. Now, this 2 pi you're seeing here, this is the angular displacement. That's a distance, the angular distance which the spacecraft is going to cover in radians. So it has got units of radians. The other bit is this omega, which we have worked out. So in that case, if you substitute, you end up having t is equals to 2 pi radians divided by 9.5 times 10 to the power minus 4 radians per second. Then you end up having a period which is being equals to 6,618 seconds. This 6,618 seconds in minutes is equals to 110 minutes and 18 seconds. So it's going to take our spacecraft 110 minutes and 18 seconds to complete an orbit at that particular height, at 20,000 meters above the moon. Is that clear? These updated notes, as you can see, final update, they are now available on Moodle. So after this class, you can go and download a fresh copy of the notes then you print it out, then you study, because you guys have got a quiz next week. I'm sure some of this stuff is going to be there. Any questions so far?
Yes, I have a question.
Yes, go ahead.
So if we have been asked to find time, we're supposed to leave the answer in seconds or in minutes?
You can leave it in seconds, but the question is, you don't have a very good idea how much 6,618 seconds is. Yeah, as a human being, if I tell you it's going to take 6,618 seconds, you have got no idea how much that time is. But if you put it in minutes, since people watch football, and they've been watching football this past June, at least you've got and the matches have been going to extra time, at least you've got an idea of what 110 minutes looks like.
All right.
Yes. You can leave it in seconds, but you can also express it in minutes if you want. Any other question? Do people have got questions? Okay, if there are no questions, then we push forward. So now I think up to this point, I think that's where we were on Thursday. So the other force which can provide centripetal force is the tension. Now, tension in a rope, when you have a mass attached to the end of a rope, like the case in this particular diagram here, you have this mass you attach to a rope, then someone is in the center here, then this mass, you rotate it, whether vertically or horizontally. The tension is going to provide the centripetal force. The tension is the one which is going to be forcing this particular object to move in a circle. So in this case, you are if it's vertical, fine, it's also the tension, but it's also, if it's horizontal, if you assume that the thing is horizontal, the circular track in which this particular object is going to be moving is going to be horizontal, then in this particular case, the centripetal force is just provided by the tension, like this, as shown by equation number 20. So we have an example of this. A 20 kg object is tied to the end of a cord and whirled in a horizontal circle of radius 1.2 at a speed of 3 revolutions per second. Assume that the cord is horizontal, i.e., so it's moving in a circle and it's flat. Neglect the weight, that gravity can be neglected. Determine the acceleration of the object, which is the centripetal acceleration, since this particular object is moving in a circle, and the other bit is the tension which is in the cord. The tension is the one which is providing the centripetal force. So we need to find what the centripetal force is, since we know the mass of the object which is being rotated in a circle, and from that centripetal force we know that that centripetal force is being provided by the tension as has been shown here. So we can work out the tension. So in this case, we have how fast the object is moving in a circle. In terms of angular, we have got 3 revolutions per second, but we do not do calculations in the revolutions per second. And you also have the mass, which is 200 grams, but we don't do calculations in grams. So we change our mass here. Our mass, which is 200 grams, we change it into kgs, so it becomes 0.2 kgs. Then also the radius, which is, we have our radius as 1.2 meters. And then we have our angular velocity, which is 3 revolutions per second. Now this 3 revolutions per second, we have to change it into radians per second. Just a minute, there is a call somewhere. Okay, let's continue. We need to admit someone. Okay, so we have our angular speed in revolutions per second. So this angular speed in revolutions per second has to be changed into radians per second. And how do you do that? So that's going to be 3 revolutions per second. It's going to be 3 revolutions divided by 1 second multiplied by 2 pi rad divided by 1 second. So in this case, with this conversion factor, this revolution and this revolution here, they'll cancel out. So you end up with 3 multiplied by 2 pi, which is going to give you 18.8 rads, then divided by second, so you have 18.8 rads per second. So you know your angular velocity. Your angular velocity is 18.8 radians per second, and you have a velocity, and you're with a radius of 1.2. So with this information, you can find out what the acceleration is supposed to be. So in that case, your centripetal acceleration, AC, is going to be equals to the radius multiplied by the angular velocity. So you end up having AC is equals to 1.2 meters multiplied by 18.8 radians per second. Sorry, 18.8 radians per second squared, like that, and you end up having your acceleration AC as 424 meters per second squared. Are we clear?
Yes, sir.
Okay, now that we have our acceleration and we know the mass of the mass attached to the rope, the mass is 0.2 kgs. So in that case, our centripetal force, we can find the centripetal force. The centripetal force FC required to keep this mass moving in a circle is going to be the mass multiplied by the centripetal acceleration, like that. So that mass is 0.2 kgs multiplied by centripetal acceleration, which is this. So we end up having a centripetal force which is approximately 85 newtons. This centripetal force, which is 85 newtons required to keep this mass moving in a circle, is being provided by the tension. So we end up having a tension which is equals to 85 newtons. Are we clear?
Yes, sir.
Okay. However, sometimes you can have a mass attached to a rope which is very heavy, such that even if you try to force this thing to move in a circle, it will not be possible. So if a heavy mass is attached to the end of the cord, the weight of the mass cannot be ignored. In this case, the mass will incline a bit downwards at an angle theta vertical, as shown in here, like this. So if your mass is heavy, you have attached like this. This as you are wheeling this thing in a circle, it will not be flat, but it will be inclined like this. So this is your rope. So it's going to be like this. Then your mass is going to go in a circle like that. Is this clear? So that is a circular path in which your mass is going to go. Repeats. There's going to with this vertical here, the string or the rope is going to make an angle theta. The string or the rope is going to make an angle theta, like that, and this mass has got a weight mg. This mass has got a weight mg, like that. Now the tension, there is tension in this rope. Okay. There's tension which is in this, excuse me, just a bit. So in this case, as you can see, there is tension in this rope. Okay, there's tension in this rope, but what is keeping this mass in a circle is not the tension, but it's this bit here. The x component of the tension, the horizontal component of the tension, which is written as t sine theta. This t sine theta is what is keeping the object moving in a circle. There is also other things like t cos theta. T cos theta is what is pulling this mass up. T cos theta is pulling the mass up, while mg, which is the weight of this particular object, is pulling the mass down. So the tension which is in the rope has got two components. It has got a vertical component, which is t cos theta. Then it has got a horizontal component, which is t sine theta, which is this side here. Are we clear? From this diagram, is it clear what's happening?
Yes, sir.
Okay, so the centripetal force is being provided by t sine theta. So in this case, the centripetal force Fc is being provided by the tensile force tension Ft multiplied by sine theta, and there is also the radius. The circle we're interested in is this one here. That is the circle we're interested in. Like that. Okay. So the radius of this circle, you can obtain the radius of this circle from the length of the rope, from the length of this rope, then using this angle. So the length of this rope is the hypotenuse, then this side is the adjacent, then this bit here, the radius, or this bit here is the opposite. So the length of the rope, which is L, then the radius of this circle is R. R is given by L sine theta, like that. So with this information, we can write our centripetal force. Fc is equals to the mass of the object moving in a circle, the speed with which it's moving in a circle squared, divided by the radius of the circle in which it's moving. Okay, where R is this bit. Then we have this. So we equate them. So we have mv squared divided by R is equals to ft sine theta, like this. With that bit, yeah. So right now, whatever the mass is, we don't know what the mass is. We are looking for the velocity. We don't know it. We also don't know the tension. So there's another thing we can do. We can look at this bit here. The t cos theta and mg. The t cos theta and mg are equal because this particular object doesn't go up, it doesn't go down, but it stays where it is like this. So this t cos theta and mg, they are equal to each other because there is no acceleration in that particular thing, in that particular direction. So we write Newton's second law of motion in the y direction. So that's going to be this resultant force multiplied by the mass of the object in the y direction, mass of the object and the acceleration in the y direction. But in the y direction, there is no acceleration. The object is not accelerating. It's only accelerating in the as it's moving in the circle like that. So in the y direction, the acceleration is 0 meters per second squared, and the weight of the object is this much, and the other component which is pulling the vertical component of the tension is t cos theta. So in that case, where this bit is the resultant force in the y direction, the m is the mass of the object, the a is acceleration. So we can write this bit, we can write this, the sum of the forces in the y is going to be equal to the ft cos theta minus Fw. If we choose the up direction to be positive and the down direction to be negative. So if we choose up, going up to be positive and down to be negative, then this is going to be positive and this bit is going to be negative. So we end up having this. So we can write our Newton's second law of motion as Ft cos theta minus Fw equals to the mass multiplied by the acceleration 0, like this. So mass times 0, so you end up having 0 here. So we end up having Ft cos theta minus Fw is equals to 0. Then you have this Ft cos theta equals to Fw. Then Ft cos theta equals to mg. Then we divide both sides by cos theta. So we divide both sides by cos theta. We end up having Ft is equals to mg cos theta. Divide mg divided by cos theta, like this. Now we now have an expression of the tensile force in terms of the weight and cos theta. So we can now replace these Ft here, because remember we have at the top here we had this. You have mv squared divided by r is equals to Ft cos theta. So now now that we have got something for Ft, we can put it there. When you put it there, we put the Ft there, so we end up having mv squared over r is equals to mg cos theta multiplied by sin theta. That's going to be mv squared over r equals to mg sin theta divided by cos theta this side. So this bit and this bit. So you end up when you factor them out, you have mg. You factor mg outside, so you have sin theta divided by cos theta, and this is going to give you tan theta there. So you end up having mv squared over r is equals to mg tan theta. So as you can see, there is the mass of the object this side, there is also the mass of the object this side. So when you cancel out the masses, you end up having v squared is equals to v squared divided by r is equals to g tan theta. You multiply by r on both sides, so you end up having v squared is equals to gr tan theta. Then, since you've got v squared, you're looking for the velocity, so you end up having v is equals to the square root of gr tan theta. So this is what you end up having. So when the mass attached to the rope is heavy, the velocity is given by the square root of gr then tan theta. Is that clear?
Yes, sir.
Okay, so with this expression, we can work out an example, which is what you have here. Example number 5. As shown in figure 5, a ball B is fastened to one end of a 24 centimeter string, and the other end is fixed at Q. The ball whirls in a horizontal circle shown in a horizontal circle shown. Find the speed of the ball in each circular path if the string makes an angle of 30 degrees to the vertical. So basically, this is the same problem we have been trying to work out. So in our case, we know the expression to use to find the velocity. The velocity v is equal to the square root of gr tan theta. Our theta is 30, our g is known, our r, this r is not the length of the string, but this r is the radius of this circular path. Okay, that's the r we're talking about. The r is the radius of this circular path. So in that case, since the string has got the length the 24 centimeters, then we can find out r. We can find your r by multiplying the length times the sine of the angle, which is going to give us this bit here. So the velocity v is going to be equal to gr tan theta. Our r is going to be 0.24 centimeters, which is 0.24 meters, multiplied by sine 30, and that's going to give us our r, which is going to be 0.12 meters. Then our g is 9.8, and our theta is 30 degrees. So in this case, v is going to be, so if we substitute in our thing, so we end up having v is equal to 9.8. V is equal to the square root of 9.8, 0.12 tan theta, and you end up having your v being equal to 0.82 meters per second. So this is going to be a velocity in meters per second. Is it clear?
Sure, sir.
Okay. Next, apart from that tension, you can also have centripetal force being provided by what is referred to as a bunking. When you've got a rod which is raised like this, usually our rods are flat, but there are some other cases where you find a rod has been raised like this. This is what is referred to as a bunked rod. So the rod is raised at an angle theta. The reason why engineers do this is because they want to use part of the weight of the car. The weight of the car is pointing down, but as the weight of the car is pointing down, as you can see in this diagram, the weight is pointing down. There is also what is referred to as a normal force. So if an object exerts weight on a surface, on a flat surface, that flat surface is going to push back against the particular object, and that's how rods work. So whatever is moving on the rod, it exerts weight on the rod, but the rod also pushes back. So the pushback by the rod is always at 90 degrees to the rod. So in this case, when you tilt the rod like this, the normal force which is pushing back is going to be in this direction. It's not going to be in the same direction as the weight, like this. Now it so happens that if the weight is in this direction, then opposite the weight, which is the vertical bit like that, then the normal force is in this direction. Just a minute. So in this case, this angle of the bunking theta here, this angle theta is the same as what you have here. The angle between this and the normal force. So when you break up this normal force into its horizontal component and also vertical component, you have got this bit here. This is what is providing the centripetal force. This bit here, the normal force multiplied by the sine. And also there is also another bit here where you have got the normal force multiplied by the cosine, which is pointing up. So this bit pointing up, which is the normal force multiplied by the cosine, is pushing the car up. It's equal to the weight. And you've got this other additional bit here, which is the normal force multiplied by the sine, which is making the car stay in a circular path. I don't know if this is it's clear. Is it clear on your end? That this normal force has got two components. It has got this component, which is providing the centripetal force. It also has got this up component here, which is pushing the car up so that the car doesn't sink into the rod. Okay. So with that, our centripetal force, as usual, Fc is equals to the mass, then velocity squared divided by r. Then this centripetal force is being provided by this component, Fn sine theta. Okay, so we end up having mv squared over r is equals to Fn sine theta, like that. Now, with this expression again, we have a similar problem where we do not know what the mass of the car is, we don't know what the velocity is, and we also don't know what the normal force is. Okay, but what we do know is that the weight of the car, which is mg, is equal to this component of the normal force, which is the normal force cos theta, and that's why the car doesn't jump up and down on the rod. So there is no acceleration in the y direction. So as the car is moving in a banking or on a rod, there is no acceleration in the y direction. So in that case, we can work out what the resultant force is in the y direction. The sum of the forces in the y direction is equal to the mass multiplied by the acceleration in the y direction. So we end up having the normal force. The forces in the y direction is equal to this Fn cos theta minus Fw. So basically it's the same process like before. So we start going through. So we end up Fn cos theta minus Fw equals to the mass of the car multiplied by the acceleration, which is 0. So we end up having Fn cos theta is equals to minus Fw equals to 0. So you end up having Fn cos theta equals to Fw, which is equals to Fn cos theta equals to mg. Then we make Fn the subject of the formula, so we end up having Fn is equals to mg cos theta, like this. So Fn is equals to mg cos theta. So this is what we have. So our normal force, we have now expressed our normal force in terms of the weight of the car and also the angle of the banking. Now, why do we need to do this? You have to remember that up here we had an expression of our centripetal force. The centripetal force mv squared divided by r is equal to Fn sine theta. So we can put back our normal force, which you have just found here. So Fn is equal to mg cos theta, like that. So we can substitute here. So when we do the substitution, we end up having mv squared over r. Then we substitute, you have mg divided by cos theta multiplied by sine theta. So we end up having mv squared over r equals to mg sine theta divided by cos theta. Then we go back to the same process we've done. Mv squared over r, mg. We factor out this thing, you end up sine theta over cos theta, which is going to give us our tan theta this side. So you have got mv squared over r is equals to mg tan theta. Then there is m on both sides. So m this side, there is m this side. So you cancel out the m's. When you cancel out the m's, you end up having v squared over r is equals to g tan theta. Then next so when you cancel, we multiply by r on both sides. When you multiply by r on both sides, you end up having v squared is equals to gr tan theta, like this. Then you take the square root on both sides. When you take the square root on both sides, you end up having v is equals to the square root of gr tan theta, like this. So in this case, the velocity of your car in your banking is going to be equals to the gravity multiplied by the radius of the banked rod multiplied by the tangent of the banking angle, which is this. So basically, this is how you get your velocity. V is equal to the square root of gr tan theta. Are we clear?
Yes, sir.
Okay. So the last question, the last example which we have, basically, example number 6, a curve of rod 30 meters A curve of radius 30 meters is to be banked so that a car may make the turn at speed of 13 meters per second without depending on friction. What must the slope of the curve be? Basically, they're asking about the banking angle. So now when it comes to banking, we know that the velocity v is equal to the square root of gr tan theta. So what they're asking us is to find what the angle is. They are asking us if the car is going to be moving at 13 meters per second and the radius of the road is 30 meters, how much should the angle be? So we get that expression. So this is what you have here. So the radius is 30 meters. They're asking us for the banking angle theta. Then we know the car is moving at supposed to move at 30 meters per second. So how much is the banking angle supposed to be? So we know that the velocity of the car v is equal to the square root of gr tan theta. So our v in this case is 13 meters per second. We're looking for theta and we know the r. So we want to get this bit here. We want to get tan theta so that we can find theta. So in this case, when you square both sides, you end up with v squared is equal to gr tan theta. Then when you divide both sides by gr, so you end up with tan theta is equal to v squared over gr. Then next we substitute. For v, we put in our 13 meters per second. For g, we put in 9.8. For r, we put in 30. So when you do that, when you make those substitutions, we end up having tan theta is equal to 13 meters per second squared, then divided by 9.8 times 30. So this thing is tan theta is going to be 169 meters squared second squared, 294 meters squared second squared, and you end up with tan theta equals to 0.57. So this bit here and that bit there, they will cancel out. So you have tan theta equals to 0.97. Then for us to find theta is just going to be equal to the tan inverse of 0.57, and that's going to give us a banking angle theta which is equal to 30. Are we clear?
Yes, sir.
Yeah, so basically we are done with this bit. Apologies for the interruptions. Some people are coming to see me. Okay, are there any questions?
All right, sir.
Any questions?
Yes, I have a question, sir.
Yes.
Actually, it's concerning the notes. Are these notes been posted on Moodle?
Yes.
The updated one.
Yes, the updated one is there on Moodle. I just posted it this morning before we started the class.
Okay, sir.
Yeah, so you can access them as soon as you can. Just download them, then you can print them out. You don't even have to rewrite these whole things. Just download the notes, then have them printed out.
All right, sir.
Okay. Any other question? Okay, so if there are no other questions, we'll stop here. So see you on Monday next week. 14 hours.
All right, sir.
Yes.
Thank you.
All right, have a good weekend.